Friedel-Crafts alkylation is an important reaction, and it's really a type of electrophilic aromatic substitution reaction. It just is making a new carbon-carbon bond, so it's powerful in that regard. Now, the carbocations are going to be formed, and they're going to be reacting as our electrophiles. So there are E plus that we're going to see reacting. And again, we're making new carbon-carbon bonds. So the observed reaction is taking a benzene. I'll just highlight an H right there. And the reactants that we're going to see here is we'll see that this is added to some type of an alkyl halide. X is a good leaving group, so chlorine, bromine, or iodine, for example. And then we need to have a Lewis acid here, so AlCl3 can be used, or FeCl3 might be used for that. And again, those are acting as our catalyst, or the Lewis acid here, to help facilitate that reaction. All right, now the product that we get is our benzene ring with an R group, right? And then of course plus HX here. So you've made a new, here, just to point this out, right, you've made a new carbon-carbon bond. So there's only a handful of ways that we do that throughout the whole year. Grignard was one of them, acetylene ions another. And this is just an additional way to do that. The mechanism is actually fairly straightforward. So if we look down below here, let's just look at an example here. Let's take tert-butyl chloride. So put a Cl group here. And what we're going to see is that reacting with AlCl3. All right, now what happens is that these electrons come over here and then bond to the aluminum. So what that's going to give us is AlCl4 minus, okay, plus this, right? And so here we have a tertiary carbocation, right? And remember, that simply is going to be your E plus here. So the rest of the mechanism looks like things that we've seen before. And so looking down below here, you have your aromatic ring reacting with that tertiary carbocation. Right, get a tert-butyl group here, positive charge here, right, moves around the ring to that position, and then swings over here, right, to this final position. And then the last step that we have is a deprotonation. So we have to lose that H atom, because remember, it's a substitution reaction, EAS, right? So the last step that we have here is our AlCl4 coming over, grabbing an H, and restoring our aromaticity to give us our alkylated benzene ring, right? And then we get our AlCl3 back there. So again, fairly straightforward reaction, not a lot of surprises to be seen there. There are some additional concerns that we have to be aware of. One of the problems is that you can have rearrangement occurring. So we'll talk about rearrangement in just a second. But the other thing that we have to worry about a little bit as far as the mechanism is that the carbocation that's formed is probably only forming for more stable carbocations. So remember, all carbocations are unstable, but secondary and tertiary or allylic are probably more stable than primary. So the free carbocation probably forms under those circumstances. But for primary, you probably form a complex. So what that complex would look like is something like this. So your chlorine would come over and basically kind of make a bond there to aluminum, and they would just stay stuck together essentially, because a primary carbocation is so high energy. And then what would happen, right, is our nucleophile would come over and grab a hold of that carbon there. So you grab that carbon, and then, right, resonance, and then the rest of the mechanism would follow the same kind of pattern there. So the other types of Friedel-Crafts reactions are going to be reactions that just generate carbocations in different ways, right? Other than having AlCl3 and an alkyl halide, for example. So we can use an alkene. So if you take an alkene and add HF, for example, you end up getting this carbocation, right? So this is going to be your E plus here, right? And then we also get F minus, and this is typically a weaker nucleophile. So if you add HBr or HI, then the iodide would attack there, and you, right, have an alkene reaction like we saw from first semester. Right. The other type of reagent that we use, and both of these are used less in our Wade textbook, but BF3. So BF3 here is going to be another example of a Lewis acid. So it's accepting electrons. So coming around here and doing something along those lines. And then collectively, that would leave this BF3OH minus, and then you have your carbocation. So again, just another way of generating that electrophile. And then the rest of the reactions, similar to what we've seen before, right? So looking at that in a little bit more detail down here below, there's your carbocation that forms, right? You have your sigma complex here, right? So your sigma complex forms, and then with the resonance in that structure. And the last step would be fluorine essentially coming over in one swoop and grabbing a hold of that H. Sometimes textbooks show this. It's like a ping pong. So that goes to fluoride, and then we come over here and grab it. So we could do the bouncy arrows, or we could just do a continuous. I tend to do the continuous line. But that gives us BF2OH, and then your final product here, right? So you get your alkylated benzene, essentially. Now, there's some limitations here. Some of the limitations I've mentioned before. So one of them is that we can have carbocation rearrangements. In fact, if we look at number 2, that's what's highlighted there. And the other thing that we have to be really cautious of here is that they only work with activated benzenes, benzene itself, and halobenzenes. So strongly deactivated aromatics cannot be used in these reactions. So nitrobenzene, benzene, sulfonic acids, phenylketones, right? All those type of things fail to react. It's a key thing to remember. And it's one of those things that just pops up over and over again because it's a good question to ask on exams, for example. Now, as far as the rearrangement thing is concerned, we have to always consider that if we have the possibility of forming carbocations. Right? So when we see these two reagents like this, we should think, okay, well, if this chlorine was to leave, that position would be primary. But instead, what can happen is we can get a hydride shift here. Right? So probably what happens here is that when this adds, this thing probably leaves. And then we get an H here shifting over to this position. Right? So, in a nutshell, what that kind of looks like, if we want to write that out in a little bit more detail, you'd have something like this, right? Where you have your chlorine here coming over and making a bond essentially here with your AlCl3, and then your H is over here. And probably what happens here is that you end up having that hydrogen kind of shift over essentially at the same time that you have the loss of the chlorine there. So probably swing this thing over here and do that, and then have chlorine get kicked off. So in a nutshell, what that gives us is this plus AlCl4 minus. Now sometimes students don't like that because there's a lot going on there. So it would be okay if you wanted to write it out like this in one step, right? That would be the loss of the chlorine, and then to show that as the second movement here to give us this, right? And in the end, they both give us that same electrophile. That's kind of the key point to recognize, okay? So if we saw that reacting, then what we would get is our final product down the line is you'd get your benzene ring plus that, right? With basically a tert butyl group on that thing. Right, and then the other thing, so that's the two things to look out for. So what about the third thing? So if we look down here below, let's look at number 3. So alkyl groups are activating for EAS, right? So we know that that's the case. Therefore, the product of these Friedel-Crafts reactions is more reactive than the starting material. So the end result is that means that multiple alkylations are difficult to avoid in like a laboratory type setting. What we typically do is draw out the monoalkylated products, though. That tends to be the pattern that you see in all organic chemistry at the sophomore level, essentially. So, looking down below here you have benzene, right, plus this alkyl halide with AlCl3. So your first product would be this. And so this, for the sake of what we're going to be doing, right, we stop here. However, in reality, this thing continues on to form the di and the triethyl isomers. Right, so with your ring in there and your ethyl here, that's an OP director. So, right, we're going to get this guy essentially here, right? And then we would get this guy here, right? And so on and so forth. Different products stemming from those, but those are your di ethyl isomers there. So the other type of reaction that we see as far as Friedel-Crafts, there's alkylation and then there's acylation. Acylation also makes a new carbon-carbon bond, except that the carbon that's attached to the ring has a carbonyl group on it. So let's look at an acyl group. An acyl group is an R group connected to a carbon and an oxygen here. And typically what we're going to be making is acid chlorides and then adding these to our rings as our reagents. Now let's take a closer look at the mechanism. So the mechanism of this thing has kind of two steps, a preliminary step to it. So we're going to take here an acid chloride and we're going to add to this AlCl3. Right? Now what's going to happen is that the chlorine's going to come over here and grab a hold of that aluminum. We've seen that happen before. You're going to get your carbonyl chlorine and then your AlCl3 here, just like this. Right, so chlorine here. That kind of gets you a plus charge there, a minus charge here. Now we often refer to this thing as the bulky electrophilic complex. Well, this can decompose. That forms AlCl4 minus, and then we get this R group. So in essence, that's happening, right? So then you get your R group, you get your carbonyl here, and then a plus charge like this. This is called the acylium ion. And it's resonance stabilized. So we come around, we can do that, right? So that would give us our R, triple bond O, plus charge down here. Right, so this right here is what we're going to be treating as our electrophile. So this electrophile is going to be what reacts in our EAS reaction. So the main reaction here is not dissimilar to what we saw before. So here's our benzene. Here you have your R group with your acylium ion here. So we're going to swing around and we're going to do that. That is going to give us our carbon, double bonded O, and your R group, just like this. Well, that's going to give us our H atom, our carbon, double bonded O, just like so, and a plus charge here. Now, I know we can draw the resonance here, so I'm just going to write plus resonance, right? You get the other resonance structures of this thing. All right, and then what we have is you have your AlCl4, so your chlorine from AlCl4 coming in. It's going to grab that H, restore aromaticity, right? Now what we're going to form here is our benzene ring, so we'll get that ring reestablished. Got your carbonyl group on there, right? And then of course plus AlCl3 plus HCl. All right, that's the main end product. So there's only one little catch here, and that is that this complex right here, because this is a Lewis base and you have a Lewis acid present, it can often form this complex where we get an oxygen essentially bonded to AlCl3. Right? That would give you a little bit of a plus and a little bit of a minus right there. It's not a big deal because the way this is usually eliminated is by adding water. So then you just get back to where you started off essentially. All right, other thing to point out here too is this step right here is often not included. So it's not often seen. If you see it there, that's what they're trying to indicate that you end up forming. Now, this reaction puts a deactivating group on our ring. Now, the other thing to point out here is that this acylation reaction involves this electrophilic complex, not typically a free acylium ion. Because it's large, typically we see pair positions predominating, right? Because it's that bulky electrophilic complex. And the last thing to point out is that just like alkylation, it doesn't really work well with deactivated systems.